Close your eyes and imagine a spacecraft hurtling through the darkness at thousands of miles per hour. It's been traveling for years, perhaps decades, covering billions of miles through a realm filled with planets, moons, asteroids, and debris. Yet somehow, impossibly, it never crashes. It never collides. It threads through the cosmic needle with perfect precision, arriving exactly where mission planners intended, sometimes after journeys lasting longer than a human lifetime. How is this possible? How do spacecraft navigate through space for decades without hitting anything? How do mission controllers on Earth guide probes to distant planets with such accuracy that they can pass within miles of a moon billions of miles away? How does the International Space Station orbit Earth thousands of times, passing through regions crowded with satellites and debris, yet remain unscathed? Tonight, we'll explore one of the most remarkable achievements of the space age: the art and science of keeping spacecraft safe as they journey through the cosmos. We'll discover why space, despite containing countless objects, is mostly empty. We'll learn how orbital mechanics makes trajectories predictable centuries in advance. We'll see how mission planners chart courses through the solar system with extraordinary precision, and how spacecraft navigate autonomously when they're too far for real-time control. This is a story of mathematics and engineering, of careful planning and brilliant improvisation, of humanity's ability to send machines on journeys we cannot take ourselves and bring them safely to destinations we've never visited. It's a testament to our understanding of physics and our ability to work with nature's laws rather than against them. So settle in, take a deep breath, and prepare to discover why the apparent danger of space travel masks a deeper truth: that the cosmos, properly understood and navigated, is one of the safest places a machine can travel. The emptiness that seems threatening is actually protective. The speeds that seem dangerous actually provide stability. And the distances that seem impossible to navigate become, with the right knowledge, as predictable as the ticking of a clock. The first and most important truth about space is one that our intuitions struggle to grasp. Space is almost incomprehensibly empty. When we look at images of the solar system or artists' illustrations of spacecraft missions, we see planets and moons and spacecraft depicted close together, compressed for visual clarity. But the reality is that the distances between objects in space are so vast that collision is extraordinarily unlikely without deliberate intent. Consider Earth's orbit around the Sun. Our planet travels through a shell of space about 94 million miles from the Sun. If we imagine this orbit as a highway, it's a circular road 590 million miles long. Earth is a car about 8,000 miles wide traveling on this enormous highway. Now, add the other planets, each on their own highway at different distances from the Sun, each moving at different speeds. The chances of two planets accidentally being in the same place at the same time are essentially zero. They would have to be precisely positioned, moving at precise speeds at a precise moment. The universe doesn't work that way. Let's make this more concrete. The International Space Station orbits Earth at an altitude of about 250 miles. Earth's circumference at that altitude is roughly 25,700 miles. The ISS is about 357 feet long, roughly the length of a football field. If we scale this down, imagine a grain of rice, the ISS, circling a basketball, Earth, at a distance of several feet. Now imagine thousands of other grains of rice, satellites, also circling the basketball at various distances and angles. Yes, there are many grains, but there's so much space between them that collisions remain rare. The asteroid belt provides another illustration. Popular culture depicts it as a dense field of tumbling rocks that spacecraft must dodge like a video game. The reality is far different. The asteroid belt, located between Mars and Jupiter, contains millions of asteroids, but it also spans an enormous volume of space, roughly 140 million miles wide and tens of millions of miles thick. The total mass of all asteroids combined is less than 4% of the Moon's mass, spread across a volume about 1 billion times larger than the Moon itself. NASA's various spacecraft have flown through the asteroid belt multiple times without special navigation. The distance between asteroids averages hundreds of thousands of miles. You could fly through the belt blindfolded, and your chances of hitting anything would be negligible. When scientists want to visit an asteroid, they don't worry about avoiding collisions, they worry about finding the asteroid in the first place. The challenge isn't dodging rocks, it's locating a specific rock in the vast emptiness. Even in the busiest region of space low Earth orbit, where most satellites operate, the density of objects is remarkably low. As of 2024, there are roughly 8,000 satellites in orbit around Earth, plus about 34,000 pieces of trackable debris larger than 10 centimeters. That sounds like a lot. But these objects are spread across a volume of space extending from about 100 miles to 22,000 miles above Earth's surface. The surface area of a shell 250 miles above Earth, where the ISS orbits, is about 209 million square miles. With roughly 2,000 objects at that altitude, that's one object per 100,000 square miles, a density far lower than cars on a highway. The emptiness of space is protective. When Voyager 1 launched in 1977, it was aimed toward Jupiter, 400 million miles away. Jupiter itself is about 88,000 miles in diameter. In the vastness of space, that's a tiny target. Yet Voyager found it not by luck, but by precise calculation. More remarkably, it then aimed for Saturn, another billion miles away, and found that too. And in all its journey, covering more than 14 billion miles over 40+ years, Voyager has never hit anything. It has never had to dodge or maneuver to avoid a collision. This is the paradox of space travel. The immense distances that make exploration difficult also make it safe. A spacecraft launched from Earth is entering an environment so empty that the main challenge isn't avoiding collisions, it's reaching anything at all. The vast majority of space contains nothing. True, there are hazards, asteroids, comets, space debris, micrometeorites, but they occupy such a tiny fraction of the available volume that encountering them requires either extraordinary bad luck or deliberate navigation. Of course, near planets and moons, the density increases. Saturn's rings, for instance, are genuinely crowded with particles. A spacecraft passing through them would face significant risk. That's why Cassini, which orbited Saturn for 13 years, mostly avoided the rings, making only a few carefully planned passes through gaps. Near Earth, the concentration of satellites and debris creates real collision risks. But even here, space is vast enough that with proper tracking and coordination, collisions remain rare events, not daily occurrences. The emptiness of space is the first layer of protection for spacecraft, but it's not the only one. Even in regions where objects are relatively numerous, other factors contribute to safety. Orbital mechanics, the physics of how objects move through space, provides another layer of protection, one that makes the paths of spacecraft and celestial bodies predictable far into the future. If space's emptiness is the first reason spacecraft rarely collide, the second is the beautiful predictability of orbital mechanics. Objects in space don't move randomly. They follow precise mathematical laws discovered by Kepler, Newton, and Einstein. These laws make the motion of spacecraft and celestial bodies as predictable as clockwork, often more predictable than anything on Earth. When a spacecraft is in orbit, it's not being held in place by engines constantly firing. It's in free fall, continuously falling toward the body it orbits, but also moving sideways fast enough that it keeps missing. This state of free fall requires no energy to maintain. An object in a stable orbit will remain in that orbit indefinitely without any propulsion. The Moon has been orbiting Earth for billions of years without engines. Asteroids orbit the Sun for billions of years without course corrections. This predictability is remarkable. If you know an object's position and velocity at one moment, you can calculate its position at any future moment with extraordinary precision. The mathematics of orbital mechanics, refined over centuries, allows mission planners to predict where a spacecraft will be years or even decades in the future. They can calculate trajectories that will bring a probe to Jupiter at a specific time, knowing Jupiter's position years in advance. They can plan gravitational assists that use one planet's gravity to redirect a spacecraft toward another planet, all calculated years before the encounter. Consider the Voyager missions again. Launched in 1977, Voyagers 1 and 2 were aimed not just at Jupiter but at specific points in space where Jupiter would be years later. The spacecraft didn't chase Jupiter, they went to where Jupiter was going to be. The calculations were so precise that Voyager 2 could perform a grand tour of the outer planets visiting Jupiter, Saturn, Uranus, and Neptune in sequence. Each planetary encounter was calculated years in advance. Each gravitational assist was planned to send the spacecraft toward the next planet. And it all worked, despite the immense distances and decade-long journey, because orbital mechanics is deterministic. This predictability extends to potential collisions. If we know the orbits of two objects, we can calculate whether they'll ever be in the same place at the same time. We can predict close approaches years in advance. For example, every object in Earth orbit is tracked by the U.S. Space Surveillance Network and other systems. Computers continuously calculate their orbits and predict conjunctions events, where two objects might come close together. When a potential collision is detected, it's usually days or weeks in advance, providing ample time to plan a maneuver. The International Space Station regularly performs debris avoidance maneuvers. When tracking predicts that a piece of space debris might pass uncomfortably close, the ISS fires its thrusters to adjust its orbit slightly, ensuring the debris misses. These maneuvers are planned days in advance based on precise orbital calculations. The debris isn't dodged in real time like avoiding a car on the highway. It's avoided through prediction and planning, made possible by the deterministic nature of orbital motion. Orbital mechanics also creates natural separation between objects. Satellites in different orbits move at different speeds and follow different paths. A satellite in low Earth orbit, 200 miles up, orbits Earth every 90 minutes. A satellite in geostationary orbit, 22,000 miles up, orbits once every 24 hours. These orbits naturally separate the satellites. They're not just at different altitudes, but moving through space along entirely different trajectories. Even satellites in similar orbits are separated by the timing of their passage. If two satellites orbit at the same altitude but one is slightly ahead of the other, they maintain that separation indefinitely. The trailing satellite doesn't catch up because both are in the same orbit, moving at the same speed. This is why satellite operators can place multiple satellites in similar orbits without collision risk. As long as they're separated along their orbital path, they remain separated. The predictability of orbits extends to natural objects too. Asteroids follow predictable paths around the Sun. We can calculate their orbits and predict their positions centuries into the future. This allows mission planners to know exactly where an asteroid will be when they want to visit it. It also allows us to predict potential Earth impacts decades in advance, providing time to plan deflection missions if needed. Of course, orbital mechanics becomes more complex when multiple gravitational bodies interact. The three-body problem, predicting the motion of three mutually gravitating objects, has no simple mathematical solution. Near planets with moons, or in regions where the Sun's gravity competes with a planet's gravity, orbits can become chaotic. But even chaos, in the mathematical sense, isn't random. It's deterministic chaos, complex, sensitive to initial conditions, but still governed by physical laws and calculable with sufficient computational power. Modern spacecraft use this understanding to navigate complex gravitational environments. The Lagrange points locations where the gravitational forces of two bodies balance provide stable parking spots for spacecraft. The James Webb Space Telescope orbits the Sun-Earth L2 point, about 1 million miles from Earth, where it can remain with minimal fuel use. Mission planners understand these subtle gravitational interactions and use them to their advantage. The clockwork predictability of orbital mechanics means that once a spacecraft is on its planned trajectory, it will generally stay there. Perturbations from gravitational interactions or solar radiation pressure cause gradual drift, requiring occasional corrections. But these effects are small and predictable. A spacecraft's orbit doesn't suddenly change. It doesn't veer off course without warning. It follows the mathematical laws of physics with the precision of a calculation, making long-duration missions possible without constant intervention. The emptiness of space and the predictability of orbits create the conditions for safe spaceflight. But translating these conditions into actual missions requires extraordinary planning. Mission designers must chart courses through the solar system that account for every gravitational influence, every source of error, every potential hazard. The trajectory of a spacecraft is not a line drawn on a map, but a mathematical solution to a complex optimization problem. Planning begins years before launch, sometimes decades. Mission designers must first identify when launch opportunities exist, the alignment of planets that makes a particular mission feasible. These launch windows occur when the target destination is positioned favorably relative to Earth. Missing a launch window might mean waiting months or years for the next opportunity, as planetary alignments repeat on predictable but infrequent cycles. The Hohmann transfer orbit is the most fuel-efficient way to travel between two circular orbits around the same body. To travel from Earth to Mars, for instance, a spacecraft follows an elliptical orbit that touches Earth's orbit at one end and Mars's orbit at the other. But this only works if Mars is positioned correctly when the spacecraft arrives. The alignment occurs about every 26 months, creating launch windows for Mars missions every 2 years. For missions to outer planets, the planning is even more complex. The Voyager missions took advantage of a rare alignment of Jupiter, Saturn, Uranus, and Neptune that occurs once every 175 years. Mission planners recognized this opportunity in the 1,960 seconds and designed a trajectory that would use gravitational assists from each planet to reach the next. The precision required was extraordinary. Voyager 2 needed to pass within specific distance ranges of each planet to receive the correct gravitational boost, all calculated years before the encounters. Modern mission planning uses sophisticated computer simulations. Designers input the initial conditions: launch date, launch energy, spacecraft characteristics, and the software propagates the trajectory forward, accounting for gravitational influences from the Sun, planets, and moons. The simulation reveals where the spacecraft will be at any future time. Designers then adjust the trajectory, tweaking launch dates, velocities, and planned maneuvers until they find an optimal path. Optimal means different things for different missions. Some missions prioritize speed, reaching the destination as quickly as possible. Others prioritize fuel efficiency, taking longer routes that require less propellant. Some missions have multiple destinations or scientific objectives along the way, requiring trajectories that pass specific locations at specific times. The planning process involves finding trajectories that satisfy all mission requirements while remaining within the spacecraft's capabilities. Gravity assists, also called gravitational slingshots, are a crucial tool in mission planning. When a spacecraft passes close to a planet, the planet's gravity can alter the spacecraft's velocity, both speed and direction. Approaching a planet in the right way can increase the spacecraft's speed relative to the Sun, allowing it to reach distant destinations without carrying massive amounts of fuel. Conversely, gravity assists can decrease speed, allowing spacecraft to be captured into orbit around a target planet. The Cassini mission to Saturn used 4 gravity assists, 2 at Venus, 1 at Earth, and one at Jupiter to reach Saturn. Each encounter was planned years in advance. The spacecraft had to arrive at each planet at precisely the right time and location to receive the correct velocity change. The cumulative effect of these assists allowed Cassini to reach Saturn with enough velocity to enter orbit, something that would have been impossible with a direct trajectory given the available launch vehicles. Gravity assists require extraordinary precision. A spacecraft must pass within hundreds or thousands of miles of a planet billions of miles away, arriving within minutes of the planned time. This precision is achieved through careful trajectory design and in-flight corrections. As the spacecraft approaches a planet, mission controllers track its position and calculate small thruster burns to adjust the trajectory, ensuring the spacecraft arrives at exactly the right place for the assist. Mission planners must also account for uncertainty. Spacecraft trajectories are subject to many small perturbing forces: solar radiation pressure, outgassing from the spacecraft, gravitational influences from distant bodies, even relativistic effects near massive planets. These perturbations cause the actual trajectory to differ slightly from the planned one. Mission designers account for this by building flexibility into the plan, reserving fuel for mid-course corrections that can compensate for accumulated errors. The planning process also considers hazards. When Cassini approached Saturn, mission planners had to chart a course through the planet's complex system of moons and rings. They identified safe corridors through the system where the risk of collision with ring particles or small moons was minimized. They planned the orbital tour to avoid regions of high dust concentration and to keep the spacecraft outside the densest parts of the rings, except for a few carefully planned passages. Similarly, missions to small bodies like asteroids or comets require careful hazard analysis. These objects can eject dust and gas, creating temporary hazards. Comets, as they approach the Sun, become active, spewing material that could damage a spacecraft. The Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko, had to constantly monitor the comet's activity and adjust its orbit to maintain a safe distance while still conducting science. The New Horizons mission to Pluto faced a different challenge. The spacecraft would pass Pluto at high speed, with only one chance to collect data. Mission planners identified potential hazards: unknown moons or debris rings around Pluto that might endanger the spacecraft. They designed the trajectory to minimize risk while maximizing scientific return. As New Horizons approached, it searched for hazards using its cameras. Finding none, it proceeded on the planned close approach trajectory, passing within 8,000 miles of Pluto's surface. Mission planning doesn't end at launch. As a mission progresses, planners update their understanding based on new data. They refine trajectory predictions, identify new scientific opportunities, and respond to spacecraft anomalies. The trajectory that exists in the planning documents before launch is a starting point, not a fixed constraint. The actual mission involves continuous replanning and optimization as new information becomes available. This iterative planning process has allowed missions to achieve extraordinary precision. The Curiosity rover landed on Mars in 2012, arriving after an 8-month journey of 354 million miles, and landed within 1.5 miles of its target, a precision of better than 0.0004%. The OSIRIS-REx mission traveled to asteroid Bennu, collected a sample from a boulder-strewn surface using a robotic arm, and returned that sample to Earth, all requiring navigation precision measured in meters across distances measured in millions of miles. The planning process is what transforms space from a vast, empty void into a navigable realm. By understanding the mathematics of orbital mechanics, by accounting for every force and every uncertainty, by building in flexibility and redundancy, mission planners create paths through space that spacecraft can follow safely for years or decades. The trajectories are not guesses or approximations, but precise mathematical solutions, calculated and recalculated until they meet every requirement of the mission. A perfectly planned trajectory is only useful if the spacecraft knows where it is and where it's going. Navigation determining a spacecraft's position and velocity is one of the most critical functions in spaceflight. Without accurate navigation, even the best plans are useless. Yet navigating in space is fundamentally different from navigating on Earth. There are no landmarks, no GPS satellites broadcasting position signals, no magnetic north to reference. Spacecraft must determine their position using more subtle cues. The primary method of spacecraft navigation is radio tracking from Earth. Ground stations around the world, NASA's Deep Space Network, DSN, ESA's STRAC, and others communicate with spacecraft and measure the radio signals traveling between Earth and the spacecraft. By analyzing these signals, engineers can determine the spacecraft's position and velocity with remarkable precision. The Deep Space Network consists of 3 complexes in California, Spain, and Australia positioned around the globe so that at least one can always communicate with any spacecraft. Each complex has multiple large dish antennas, including 70-meter dishes that can communicate with spacecraft at the edge of the solar system. These antennas both transmit commands to spacecraft and receive telemetry and science data from them. But the antennas also perform a less obvious function. They precisely measure the spacecraft's motion. When a ground station transmits a signal to a spacecraft, the signal's frequency is precisely known. The spacecraft receives this signal, processes it, and transmits a signal back to Earth. The ground station receives the returning signal and measures its frequency. Due to the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes the frequency of the returning signal is shifted based on the spacecraft's radial velocity, how fast it's moving toward or away from Earth. By measuring this Doppler shift, engineers can determine the spacecraft's velocity along the line of sight from Earth to a precision of fractions of a millimeter per second. By measuring the time delay between transmission and reception, they can determine the spacecraft's distance to a precision of meters. Multiple measurements from different ground stations provide enough information to determine the spacecraft's full three-dimensional position and velocity. This is how missions like Voyager, now more than 14 billion miles from Earth, are still navigated. Radio signals from DSN travel to Voyager at the speed of light, taking over 21 hours to arrive. Voyager receives the signal, processes it with 1,970 seconds technology, and transmits a response. That response takes another 21 hours to return to Earth. From this 42-hour round-trip communication and the Doppler shift of the signals, engineers can determine Voyager's position in the outer solar system to within a few kilometers. For spacecraft closer to home, navigation is easier but still requires precision. The International Space Station's orbit is tracked continuously by ground stations. Its position is known to within a few meters, and its velocity to within millimeters per second. This precision is necessary because the ISS orbits Earth every 90 minutes, traveling at 17,500 miles per hour. At that speed, a small error in position or velocity becomes a large error very quickly. Navigation becomes more challenging when spacecraft are near other bodies. When a spacecraft approaches a planet or moon, that body's gravity perturbs the trajectory. These perturbations must be measured and incorporated into navigation solutions. As Cassini orbited Saturn, the gravitational tugs of Saturn's many moons constantly altered its trajectory. Engineers used radio tracking to measure these perturbations, which actually helped them determine the moon's masses more accurately than any other method. Some spacecraft carry their own navigation instruments. Star trackers, cameras that image the star field and compare it to an onboard catalog, can determine a spacecraft's orientation. By knowing which stars appear where in the camera's field of view, the spacecraft can determine which direction it's pointing to. Extremely high precision. This is crucial for pointing scientific instruments, antennas, and solar panels. Inertial measurement units, IMUs, use gyroscopes and accelerometers to track a spacecraft's rotation and acceleration. By integrating these measurements over time, the spacecraft can estimate how its position and orientation have changed since the last reference point. IMUs are subject to drift, small errors that accumulate over time, but for short-term navigation and attitude control, they're invaluable. Some missions use optical navigation. Cameras image the target body, a planet, moon, or asteroid, and measure its position relative to background stars. As the spacecraft approaches, the target grows larger in the camera field of view, and its motion across the star field changes. Software analyzes these images to determine the spacecraft's position relative to the target. This technique was crucial for New Horizons during its Pluto flyby and for OSIRIS-REx during its approach to asteroid Bennu. The Mars rovers use a combination of techniques. They receive navigation solutions from Earth based on radio tracking, but they also navigate locally using cameras and wheel odometry. As a rover drives, it images the terrain ahead, identifies hazards, and plans a safe path. It measures wheel rotations to estimate how far it has traveled. By combining these local measurements with periodic updates from Earth-based tracking, the rovers navigate across kilometers of Martian terrain. Autonomous navigation is becoming increasingly sophisticated. The Ingenuity helicopter on Mars navigates autonomously during its flights. It uses a camera pointed downward to track features on the ground, estimating its velocity and position. An IMU tracks its orientation. Onboard software combines these inputs to keep the helicopter stable and on course. All of this happens autonomously because radio signals take many minutes to travel between Earth and Mars, too long for human controllers to pilot the helicopter in real time. Deep space missions increasingly rely on autonomous navigation as they venture farther from Earth and communication delays grow. When New Horizons flew past Pluto, it executed pre-planned observations autonomously because the 9-hour round-trip light time made real-time control impossible. The spacecraft had to navigate, point its instruments, and collect data without human intervention, only reporting back to Earth after the fact. Future missions will push autonomy further. Spacecraft that explore the moons of Jupiter or Saturn will face harsh radiation environments and long communication delays. They'll need to navigate and respond to hazards autonomously. Missions to interstellar space, if they're ever launched, would be essentially autonomous communication delays of years, would make real-time control meaningless. Yet even with autonomous navigation, ground-based tracking remains crucial. It provides the absolute position reference that autonomous systems need to correct for accumulated errors. It allows mission controllers to verify that the spacecraft is on the intended trajectory and to plan mid-course corrections if needed. The combination of ground-based tracking and autonomous navigation gives spacecraft the best of both worlds: the precision and global perspective of Earth-based systems, and the responsiveness and local awareness of onboard systems. Navigation is what keeps spacecraft on course through the vast emptiness of space. It's what allows them to arrive at distant destinations at precisely the right time. It's what enables orbit adjustments to avoid debris. It's the invisible thread connecting spacecraft to their ground teams, providing the information needed to guide these machines through years-long journeys across the solar system. While most of space is empty, Earth's immediate vicinity is becoming increasingly crowded. Decades of space activity have created a population of satellites and debris in orbit around our planet. Managing this crowded environment, ensuring satellites don't collide with each other or with debris, is one of the most challenging aspects of modern spaceflight. Space debris consists of non-functional objects in Earth orbit, defunct satellites, spent rocket stages, and collision fragments. Tracking systems monitor about 34,000 objects larger than 10 centimeters, but an estimated 130 million pieces larger than 1 millimeter exist. Most are too small to track, but large enough to damage spacecraft. The debris population concentrates in specific regions. Low Earth orbit, LEO, from about 100 to 1,200 miles altitude, contains the most objects. Geostationary orbit, GEO, at 22,236 miles altitude, is also crowded. Objects in orbit move at miles per second. A 1 centimeter paint fleck has the kinetic energy of a bowling ball at 60 miles per hour. Collisions can create cascading debris, a threat known as Kessler syndrome. Several notable events have contributed to the debris population. In 2009, the defunct Russian satellite Cosmos 2251 collided with the operational U.S. communications satellite Iridium 33. The collision, at 26,000 miles per hour, destroyed both satellites and created over 2,300 trackable fragments. In 2007, China tested an anti-satellite weapon by destroying one of its own weather satellites, creating over 3,000 trackable fragments. These events significantly increased the debris population and the collision risk for all space operations. To manage collision risk, space agencies and satellite operators rely on tracking and conjunction assessment. The U.S. Space Surveillance Network tracks all objects larger than about 10 centimeters in LEO and larger than 1 meter in GEO. Tracking data is shared with satellite operators through the space-track.org website and through direct notifications when close approaches are predicted. Similar tracking systems operate in other countries. Conjunction assessment involves predicting when two objects might pass close together. Software continuously computes the orbits of all tracked objects and identifies conjunctions events where two objects come within a defined threshold distance. For the International Space Station, any object predicted to pass within a rectangular box 2.5 miles long, 30 miles wide, and 30 miles deep is flagged for further analysis. When a potential collision is identified, analysts calculate the probability of collision. This probability depends on the uncertainty in both objects' orbits, the size of the objects, and the geometry of the encounter. If the probability exceeds a threshold, typically 1 inch 10,000 for crewed spacecraft, higher for uncrewed spacecraft, operators decide whether to maneuver. The ISS performs debris avoidance maneuvers several times per year on average. The process begins when conjunction assessment predicts a close approach. Flight controllers analyze the situation, determining whether a maneuver is needed and if so, when and how large. The ISS has multiple spacecraft docked to it: Russian Progress cargo ships, US, commercial cargo vehicles, Soyuz crew capsules, any of which can fire their engines to adjust the station's orbit. The maneuver is typically executed days before the predicted close approach, shifting the ISS's orbit enough to ensure the debris misses by a safe margin. Sometimes there isn't time for a planned maneuver. In rare cases, when a potential collision is identified with insufficient notice for a maneuver, the crew moves to their return spacecraft and closes hatches, ready to evacuate if necessary. This happened in 2021, when debris from a Russian anti-satellite test passed close to the ISS with little warning. Fortunately, the debris missed, but the event highlighted the growing hazard posed by untracked or suddenly created debris. Commercial satellite operators also perform collision avoidance maneuvers. Companies like SpaceX, operating constellations of hundreds or thousands of satellites, have developed automated systems for conjunction assessment and maneuver planning. When a potential collision is detected, these systems automatically calculate an avoidance maneuver and execute it without human intervention. This automation is necessary because manually assessing every potential conjunction for thousands of satellites would be impossible. Collision avoidance requires international cooperation. Satellites are operated by agencies and companies in many countries. Debris doesn't respect national boundaries. An object in orbit can threaten any satellite, regardless of who operates it. Space Surveillance Network data is shared internationally, and agencies coordinate to avoid collisions. When two operational satellites risk colliding, their operators communicate to decide who will maneuver. The effectiveness of collision avoidance depends on accurate tracking and prediction. For objects that are tracked, collision risk can be managed. But many small debris pieces aren't tracked; they're too small for ground radars to detect reliably. These objects pose an unavoidable background risk. Spacecraft designs incorporate shielding to protect against small debris impacts. The ISS has Whipple shields, layers of material that cause small debris to fragment and vaporize before penetrating the station's hull. Looking forward, the debris problem will worsen without action. More satellites are being launched than ever before. Mega constellations, groups of thousands of satellites providing global internet coverage, are rapidly increasing the population of active spacecraft in LEO. Even if all new satellites are designed to deorbit at end of life, the existing debris population will persist for decades or centuries, depending on altitude. Active debris removal missions that capture and deorbit defunct satellites or large debris is being developed, but remains challenging and expensive. Several technology demonstrations have occurred, and commercial companies are developing debris removal services. Regulations now require new satellites to deorbit within 25 years of end of mission, limiting future debris accumulation. But managing the existing debris population will require sustained effort and international cooperation. Despite the challenges, the space community has successfully managed orbital debris for decades. Collisions are rare; only a handful have occurred in the entire history of spaceflight. Debris avoidance has become routine, a normal part of space operations. The International Space Station, orbiting through one of the most crowded regions of space, has operated safely for over 2 decades. While the debris problem requires continued vigilance, it hasn't prevented space exploration or made Earth orbit unusable. With proper tracking, planning, and international cooperation, the orbital environment remains navigable. When spacecraft leave Earth orbit and venture into interplanetary space, they enter a realm where the margin for error is measured in meters across distances of millions or billions of miles. The precision required for interplanetary navigation is extraordinary, yet missions routinely achieve it, arriving at distant planets and moons at precisely planned times and locations. How is such precision possible? The journey begins with trajectory design, as discussed earlier. But design is only the first step. Once a spacecraft launches, the actual trajectory will differ slightly from the planned one. Launcher performance varies slightly. Upper stages don't always deliver exactly the intended velocity. The spacecraft's mass might differ from estimates. Small forces act on the spacecraft's solar radiation pressure, outgassing thermal radiation that perturb the trajectory. These deviations, though small, accumulate over time and distance. This is where trajectory correction maneuvers, TCMs, come in. TCMs are small thruster burns performed during the cruise phase of a mission to adjust the trajectory and compensate for accumulated errors. Most interplanetary missions perform multiple TCMs, especially early in the mission when small corrections can make large differences in the arrival conditions at the destination. Consider the Mars Science Laboratory (MSL) mission that delivered the Curiosity rover to Mars in 2012. After launch, the spacecraft was on a trajectory that would intercept Mars, but not accurately enough for a safe landing. Over the 8-month cruise, the mission performed 6 TCMs. The first 3 weeks after launch adjusted the trajectory to target Mars more precisely. Subsequent TCMs refined the targeting, accounting for navigation errors and execution errors from previous burns. The final TCM, just days before Mars arrival, performed last-minute fine-tuning to ensure Curiosity arrived at exactly the right entry point. Each TCM is planned using the latest navigation data. After a maneuver, ground stations track the spacecraft and determine the new trajectory. Analysts compare this to the desired trajectory and plan the next correction. This iterative process measure, adjust, measure again continues throughout the mission, gradually reducing trajectory errors to acceptable levels. The size of TCMs varies. Early in a mission, when small corrections can significantly change the arrival conditions, TCMs might be relatively large, tens or hundreds of meters per second velocity change. As the spacecraft approaches its target, TCMs become smaller, making finer adjustments. The final TCMs might change velocity by only centimeters per second, yet these tiny adjustments can shift the arrival point by hundreds of miles. Timing is crucial. A TCM performed early in the mission, when the spacecraft is still close to Earth, can achieve a larger effect with less fuel than the same correction made later. This is why mission planners front-load TCMs, performing several early in the cruise phase. By the time the spacecraft approaches its destination, the trajectory should need only minor tweaks. Fuel budget is always a concern. Every TCM uses propellant, and spacecraft carry only a finite amount. Mission designers allocate a fuel budget for TCMs based on statistical models of likely trajectory errors. They reserve fuel for contingencies, unexpected deviations that require larger corrections. If TCMs use less fuel than budgeted, the saved fuel can extend the mission or enable additional maneuvers later. Optical navigation becomes crucial as spacecraft approach targets. Cameras image the destination against background stars, measuring position discrepancies to refine trajectory solutions. New Horizons used optical navigation extensively during its Pluto approach, achieving a flyby altitude within 45 miles of the 7,800-mile target after a 3 billion-mile journey, an error of less than 0.6%. Missions to small bodies require even greater precision. OSIRIS-REx navigated to asteroid Bennu, only 500 meters across, using optical navigation and iterative trajectory refinement. Upon arrival, it entered orbit around Bennu, requiring precise knowledge of both spacecraft and asteroid positions. Landing on other worlds demands ultimate precision. Entry, descent, and landing sequences are choreographed to the second. Curiosity's Mars landing involved atmospheric entry at 13,000 miles per hour, parachute deployment, powered descent, and a sky crane lowering the rover on cables. After a 354 million-mile journey, Curiosity landed within 1.5 miles of its target precision of 0.0004%. Some missions require not just precision but sustained accuracy over years. The Juno mission orbits Jupiter in a highly elliptical orbit, designed to avoid the planet's most intense radiation belts, while still allowing close passes of the planet for science observations. Each orbit brings Juno within a few thousand miles of Jupiter's cloud tops before swinging back out to a distance of 5 million miles. Maintaining this orbit requires precise burns at each closest approach, adjusting the trajectory to set up the next orbit. Over years of operations, these maneuvers have kept Juno on track, demonstrating sustained navigational precision in Jupiter's complex gravitational environment. The techniques of interplanetary navigation have been refined over decades of missions. Each mission learns from previous ones, improving models of spacecraft behavior, force perturbations, and target body properties. Navigation software becomes more sophisticated, incorporating better statistical methods for estimating uncertainty and planning optimal maneuvers. Ground station networks become more sensitive and precise in their tracking measurements. The result is a continuous improvement in navigation accuracy, enabling ever more ambitious missions to ever more distant and challenging destinations. Yet, even with all this precision, interplanetary navigation retains an element of exploration. Destinations are often poorly known, their exact masses, gravitational fields, and orbital properties uncertain. The environment between planets contains surprises, unexpected solar wind effects, micrometeoroid impacts, thermal variations. Spacecraft themselves behave in ways not fully predicted. Components age, materials degrade, thrusters perform slightly differently than models predict. Navigation is thus not a purely mathematical exercise, but a continuous process of measurement, analysis, and adaptation, blending calculation with observation, precision with flexibility, planning with improvisation. It's an art as much as a science, practiced by teams of dedicated engineers who guide spacecraft through the solar system with extraordinary skill. One of the most elegant techniques in spaceflight is the gravitational assist, also called a gravity assist, gravitational slingshot, or swing by. This maneuver uses a planet's gravity to alter a spacecraft's trajectory and velocity without using fuel. It's a way to borrow energy from a planet's orbital motion, allowing spacecraft to reach destinations that would otherwise be inaccessible with available rocket technology. Mastering gravitational assists has been crucial to exploring the outer solar system. The concept is straightforward but counterintuitive. When a spacecraft approaches a planet, the planet's gravity pulls on the spacecraft, accelerating it. As the spacecraft recedes from the planet, gravity slows it down. In the planet's reference frame, the spacecraft enters and exits with the same speed. It seems like nothing is gained. But in the Sun's reference frame, something remarkable happens. The planet is orbiting the Sun at high-speed Earth at about 67,000 miles per hour, Jupiter at about 29,000 miles per hour. When a spacecraft approaches a planet, it's not just interacting with the planet's gravity, it's also interacting with the planet's motion through space. The spacecraft can steal some of the planet's orbital energy, increasing its own velocity relative to the Sunday, or it can give energy to the planet, slowing down relative to the Sunday. The key is the geometry of the encounter. If a spacecraft approaches a planet from behind relative to the planet's orbital motion and passes in front of the planet, the gravitational interaction accelerates the spacecraft in the direction of the planet's motion. The spacecraft exits the encounter, moving faster relative to the Sun than it entered. Conversely, if the spacecraft approaches from ahead and passes behind the planet, it's slowed down relative to the Sunday. The amount of velocity change depends on the planet's mass, the spacecraft's velocity, and how close the spacecraft passes to the planet. Jupiter, with its enormous mass, can provide velocity changes of many miles per second. Smaller planets provide smaller changes. By carefully planning the encounter geometry, mission designers can achieve specific velocity changes without using any propellant. The Voyager missions demonstrated the power of gravitational assists. Voyager 2, launched in 1977, used assists from Jupiter, Saturn, Uranus, and Neptune to reach the outer solar system. Each encounter changed the spacecraft's trajectory, aiming it toward the next planet. The assists also increased Voyager 2's velocity, allowing it to complete its grand tour in 12 years, a journey that would have taken decades without assists if it were possible at all. The Jupiter assist was particularly important. Voyager 2 approached Jupiter from below its orbital plane, passed close to the planet, and was deflected northward while also gaining speed. This encounter aimed the spacecraft towards Saturn while increasing its velocity by about 8 miles per second relative to the Sunday. The Saturn encounter then redirected Voyager 2 toward Uranus, and the Uranus encounter aimed it toward Neptune. Each assist was precisely calculated years in advance to ensure the spacecraft arrived at each planet at the right place and time for the next encounter. Cassini's journey to Saturn involved 4 gravitational assists, 2 at Venus, 1 at Earth, and 1 at Jupiter. The mission used a Venus-Earth-Jupiter VVEJ trajectory. After launch in 1997, Cassini looped back toward Venus, using a gravity assist to increase its velocity. It then returned to Venus for a second assist, gaining more speed. Next, it swung by Earth, using our planet's gravity for another boost. Finally, it flew by Jupiter in 2000, receiving a massive velocity increase that sent it on to Saturn, where it arrived in 2004. Each Cassini assist required precise navigation. The spacecraft had to arrive at each planet at exactly the right time and location, within minutes and miles after a journey of years and millions of miles. Small errors in one encounter would propagate to subsequent encounters, potentially missing planets altogether. Mission controllers performed trajectory corrections between encounters using radio tracking data to refine the spacecraft's path and ensure it arrived at each assist with the correct geometry. Gravitational assists can do more than change speed. They can also change direction, bending a spacecraft's trajectory in ways that would be impossible or prohibitively expensive with thrusters alone. The Ulysses mission, designed to study the Sun's poles, used a Jupiter gravity assist to change its orbital plane. Launched by the Space Shuttle in 1990, Ulysses flew to Jupiter, passed close to the planet, and was deflected out of the ecliptic plane, the plane of the planet's orbits. This allowed Ulysses to orbit the Sun in a polar orbit, passing over the Sun's north and south poles, something impossible to achieve with rocket propulsion alone. Gravity assists can also be used to slow down. When Galileo arrived at Jupiter in 1995, it needed to slow down enough to be captured into orbit. A direct trajectory from Earth would have brought Galileo to Jupiter with too much velocity to be captured without an enormous amount of fuel. Instead, Galileo used gravitational assists at Venus and Earth to shape its trajectory, arriving at Jupiter with just the right velocity to enter orbit after a rocket burn. Even smaller bodies can provide useful assists. The Rosetta mission, traveling to comet Churyumov-Gerasimenko, used assists from Earth and Mars. Messenger, which orbited Mercury, used 6 gravitational assists, 1 at Earth, 2 at Venus, and 3 at Mercury itself to slow down enough to enter Mercury orbit. Using Mercury's own gravity to shed velocity was far more fuel efficient than using thrusters alone. Planning gravitational assists requires sophisticated simulation and optimization. Designers must find trajectories that thread through the solar system, passing specific planets at specific times and locations, achieving specific velocity changes, all while satisfying mission constraints. This is a multi-dimensional optimization problem with many variables and constraints. Modern software can search through millions of possible trajectories to find optimal solutions, but the process still requires human insight and engineering judgment. Executing gravitational assists requires precision and adaptability. As a spacecraft approaches a planet for an assist, mission controllers track its position continuously and plan trajectory corrections to ensure it arrives with the correct geometry. They must also account for uncertainty in the planet's position and mass. In some cases, moons of the planet provide additional gravitational perturbations that must be modeled and compensated for. Gravitational assists have enabled missions that would otherwise be impossible. Without them, exploring the outer solar system would require enormous spacecraft with massive fuel loads, making launches prohibitively expensive if not infeasible. By leveraging planetary gravity, missions can reach distant destinations with existing launch vehicles and realistic fuel budgets. The technique turns the solar system itself into infrastructure, using planets as stepping stones to distant worlds. Looking ahead, gravitational assists will remain crucial for ambitious missions. Future missions to the outer solar system, to Kuiper Belt objects beyond Neptune, or to the interstellar medium will likely use complex multi-assist trajectories. Missions might use assists from asteroids, or even the Sun itself, solar obirth maneuvers that dive close to the Sun to gain velocity. As we venture farther into space, mastering gravity's gift becomes ever more important, turning the solar system's architecture into an ally in our exploration of the cosmos. As spacecraft venture farther from Earth, the finite speed of light becomes a fundamental constraint. Radio signals travel at 186,000 miles per second, fast by human standards, but slow on cosmic scales. Light takes about 1.3 seconds to travel from Earth to the Moon, 8 minutes to reach the Sun, and over 5 hours to reach Pluto. This communication delay profoundly affects how spacecraft are controlled and how they navigate. Near Earth, where light time delays are seconds or minutes, ground controllers can maintain relatively direct control of spacecraft. Commands are sent from ground stations, reach the spacecraft quickly, and the spacecraft responds. If something goes wrong, operators can react within minutes. The ISS, for instance, orbits 250 miles above Earth, a light time delay of about 1 millisecond. Effectively instantaneous communication allows continuous real-time monitoring and control. But as distance increases, real-time control becomes impossible. When New Horizons flew past Pluto, the round-trip light time was over 9 hours. A command sent from Earth would take 4.5 hours to reach the spacecraft, and the response would take another 4.5 hours to return. By the time controllers saw what was happening at Pluto, it had happened 4.5 hours earlier. By the time their commands reached the spacecraft, another 4.5 hours had passed. In that 9-hour round trip, New Horizons had traveled over 1 million miles. For the Pluto flyby, this meant New Horizons had to operate autonomously. Mission planners programmed a detailed sequence of commands into the spacecraft's computer before the encounter. At specific times, the spacecraft would point its instruments at specific targets, take images, measure particles and fields, and store the data on board. If something unexpected happened, if the spacecraft detected a hazard or a system malfunction, it had to respond autonomously using pre-programmed fault protection routines. This autonomous operation was risky. New Horizons had one chance to observe Pluto as it flew past at 31,000 miles per hour. If something went wrong during the flyby, there was no time for Earth-based troubleshooters to intervene. The spacecraft had to execute its programmed sequence flawlessly, dealing with any problems on its own. Mission planners spent years preparing, simulating every possible scenario, programming responses for foreseeable problems, and building in margins for unforeseeable ones. The flyby succeeded brilliantly. New Horizons executed its autonomous sequence, collected data on Pluto and its moons, and began transmitting that data back to Earth. The transmission itself took over a year because of the limited data rate, only a few kilobits per second at Pluto's distance. But the data arrived, revealing Pluto in unprecedented detail, validating years of planning and the spacecraft's autonomous capabilities. Voyagers 1 and 2 face even greater communication challenges. Voyager 1, now beyond 14 billion miles from Earth, experiences a one-way light time of over 21 hours. Communication is incredibly slow. Commands take 21 hours to arrive, and responses take 21 hours to return. The data rate is minuscule, measured in bits per second. Yet Voyager continues operating, executing commands, collecting data on the interstellar environment, and transmitting its findings back to Earth. At these distances, spacecraft must operate with high degrees of autonomy, but not necessarily intelligence. Voyagers are not artificially intelligent. They follow pre-programmed instructions and simple decision rules. But they are autonomous in that they can detect problems, enter safe modes, and maintain basic functionality without human intervention. This autonomy is built on layers of redundancy and fault protection. Fault protection systems monitor spacecraft health constantly. They check temperatures, voltages, pressures, and component status. If a parameter goes out of range, the system responds according to pre-programmed rules. It might switch to a backup component, adjust power usage, or enter a safe mode where the spacecraft orients its solar panels toward the Sun, points its antenna toward Earth, and waits for instructions. Mars rovers demonstrate more sophisticated autonomy. Curiosity and Perseverance use autonomous navigation to drive across the Martian surface. When given a destination, they plan a path, identify hazards using cameras and laser rangefinders, and drive toward the goal without constant human oversight. This is necessary because the 20-minute round-trip communication delay to Mars makes real-time remote driving impossible. The autonomy is bounded. Rovers don't explore freely. They follow high-level instructions from Earth-based drivers who analyze terrain images and identify safe driving routes. But within those routes, rovers navigate autonomously, stopping if they encounter unexpected hazards, working around obstacles, and reporting their progress. This blend of autonomous and teleoperated control maximizes both safety and productivity. The Ingenuity Mars helicopter demonstrates even more autonomy. During its flights, Ingenuity navigates entirely autonomously. Before each flight, operators upload a flight plan specifying altitude, heading, and duration. During the flight, Ingenuity executes the plan, using onboard sensors and processing to maintain stability and navigate. It tracks ground features with a downward-facing camera, uses an IMU to measure orientation and acceleration, and runs flight control algorithms on board to keep itself stable and on course. All of this happens without human intervention because there's no time for remote piloting. Deep space missions increasingly use autonomous navigation and decision-making. The Europa Clipper mission, planned to orbit Jupiter and make close flybys of Europa, will operate in Jupiter's intense radiation environment where electronics are stressed and failures more likely. The spacecraft will need high levels of autonomy to handle problems and continue operating when communication with Earth is interrupted or impossible. Future missions to the outer solar system and beyond will push autonomy further. A mission to Neptune's moon Triton, for instance, would face a 4-hour one-way communication delay. A lander on Triton would need to autonomously handle landing, surface operations, and anomalies without real-time support from Earth. Missions to interstellar space probes traveling to nearby stars would face communication delays of years. They would operate almost entirely autonomously, with only infrequent updates from Earth and no possibility of real-time control. Developing this autonomy is challenging. Spacecraft operate in extreme environments under harsh conditions. They must function reliably for years or decades. Autonomous systems must be robust against unforeseen circumstances, able to recognize and respond to problems, yet not so sensitive that they respond to false alarms. Engineers test these systems extensively, simulating missions in ground facilities, running millions of scenarios to identify edge cases and validate responses. Artificial intelligence and machine learning are beginning to play roles in spacecraft autonomy. Onboard AI could analyze science data, identify interesting features, and adjust observation plans to study them. It could predict equipment failures and adjust operations to extend mission lifetime. It could optimize resource usage, power, fuel, data storage to maximize science return. These capabilities are still being developed, but future missions will likely carry AI systems that make them more adaptable and capable. Yet autonomy has limits. Spacecraft can't repair themselves yet. They can't redesign their missions or invent new ways to achieve objectives when plans fail. They execute the capabilities built into them by engineers. The intelligence is in the design, testing, and programming done before launch. Autonomy extends human ingenuity across space and time, allowing spacecraft to operate far from Earth. But it's ultimately human intelligence, encoded in software and hardware, that enables these machines to function. The combination of ground control and spacecraft autonomy represents a partnership between humans and machines. Ground controllers provide high-level planning, strategic decisions, and problem-solving when time permits. Spacecraft provide real-time response, local awareness, and continuous operation when communication is delayed or impossible. Together, they achieve what neither could alone: exploration of distant worlds despite the tyranny of distance and the crawl of light across the cosmic void. Despite careful planning, accidents in space have happened. The most significant collision occurred on the 10th of February 2009 when Iridium-33, an operational satellite, collided with defunct Cosmos 2251 over Siberia at 490 miles altitude. Both satellites were destroyed, creating over 2,300 trackable fragments. The collision highlighted conjunction assessment weaknesses. Both objects were tracked, but the collision probability was calculated as low. By the time the risk was fully appreciated, there wasn't time to maneuver. The resulting debris clouds persist today, creating ongoing collision hazards. Deliberate destructions compound the problem. China's 2007 anti-satellite test destroyed a weather satellite, creating over 3,000 trackable fragments. Russia's 2021 test created 1,500 more, with debris passing through the ISS orbit. These preventable events significantly increased collision risks for all space operations. Learning from accidents has improved safety. Conjunction assessment is now routine. Spacecraft designs include better shielding. Missions plan collision avoidance as standard procedure. Yet, risks remain as the debris population grows and more satellites launch annually. As space becomes more crowded, managing the orbital environment grows increasingly challenging. The future depends on robust systems for tracking, collision assessment, coordination, and potentially debris removal. Tracking improvements are a priority. New radar and optical systems are being deployed to monitor smaller objects. Commercial companies are entering space tracking, and space-based tracking satellites are being developed to complement ground systems. Better conjunction assessment is needed. Systems that more accurately predict close approaches and calculate collision probabilities. Automated coordination among operators is essential as constellations grow. SpaceX's Starlink, with thousands of satellites, uses automated systems that receive conjunction data and autonomously maneuver when needed. International cooperation is crucial since space is a global commons. The UN Committee on the Peaceful Uses of Outer Space provides discussion forums, though enforcement remains limited. National regulations are evolving. The U.S. now requires satellites to deorbit within 5 years of mission end. Active debris removal is moving toward reality. ESA's Clear Space 1 mission will demonstrate debris capture and deorbiting. Commercial companies are developing removal services, though economics remain challenging. On-orbit servicing could extend satellite lifetimes, reducing the rate at which spacecraft become debris. The fundamental challenge is economic and political. Debris is a tragedy of the commons. Without mechanisms to internalize costs through regulations or incentives, accumulation will continue. Yet progress is being made through increased awareness, routine debris avoidance, and new technologies. The goal is not eliminating all risk but managing it to acceptable levels, developing traffic management systems appropriate to the orbital environment. We began with a question: why do spacecraft, hurtling through space at thousands of miles per hour for years or decades, never crash? We've explored the answer through multiple perspectives: the emptiness of space, the clockwork predictability of orbits, the precision of trajectory planning, the sophistication of navigation systems, the coordination required to avoid debris, the techniques of gravitational assists, the autonomy of distant spacecraft, and the lessons learned from rare accidents. The answer, ultimately, is that spacecraft rarely collide because spaceflight, properly practiced, is a discipline of extraordinary care and precision. Every mission is planned in meticulous detail. Every trajectory is calculated and recalculated. Every potential conjunction is assessed. Every hazard is identified and, where possible, avoided. This care is not optional. The harsh environment of space, the immense distances, and the vast energies involved leave no room for carelessness. Yet the deeper answer is that space itself aids in this safety. The very emptiness that makes space seem dangerous, the absence of air, the void between worlds, actually protects spacecraft. There's so much nothing that hitting something requires either great misfortune or deliberate intent. The distances are so vast that objects rarely occupy the same space at the same time. The speeds are so high that encounters are fleeting. The physics is so predictable that trajectories can be calculated far in advance. This is the paradox at the heart of spaceflight. Space seems hostile and dangerous, yet it's also remarkably forgiving. A spacecraft can travel for decades, billions of miles, and never encounter anything larger than a dust grain. It can pass through the asteroid belt without seeing an asteroid. It can orbit Earth thousands of times through a region containing thousands of other objects and never collide. This paradox arises because our intuitions, formed on Earth, where the environment is dense and crowded, mislead us about space, which is sparse and empty. But space is not entirely safe, and spacecraft are not invulnerable. Collisions have occurred, debris accumulates. As space becomes more crowded, the risk increases. The safety of spaceflight is not automatic, but achieved through constant vigilance, careful planning, and sophisticated systems. It's a testament to human ingenuity that we've made space navigable, that we can send machines on multi-year journeys with confidence they'll arrive safely, that we can operate space stations and satellite constellations in crowded orbits without constant collisions. The spacecraft that journey through the solar system carry with them the accumulated knowledge of centuries of astronomy, physics, and engineering. They embody our understanding of orbital mechanics, our mastery of trajectory optimization, our skills in navigation and control. They represent the collaboration of thousands of people, scientists, engineers, mission planners, flight controllers, working together to guide machines through the cosmos. Each successful mission is a small miracle of planning and execution, a triumph of human capability over cosmic distance. As you drift towards sleep, consider the spacecraft currently traveling through the solar system. Voyager, 14 billion miles away, still transmitting faint signals after 47 years in space, having passed through more emptiness than most missions will ever see. The ISS, orbiting overhead every 90 minutes, a complex of modules and spacecraft moving as one, maneuvering occasionally to avoid debris but mostly gliding peacefully through the void. Perseverance, rolling across the Martian surface, navigating autonomously through rocky terrain, extending human reach to another world. JWST, orbiting a mathematical point in space where gravity balances, peering at the earliest galaxies, stable and precise despite the complexity of its environment. These spacecraft don't crash not because they're lucky, but because they're guided. They follow paths carved from mathematics and physics. They navigate using signals and sensors. They respond to control from Earth or act autonomously when communication delays demand it. They embody decades of experience and countless lessons learned. They demonstrate that the cosmos, vast and indifferent as it may be, can be navigated by those who understand its laws and respect its scale. The question, why do spacecraft never crash, thus finds its answer not in a single explanation, but in the totality of spaceflight practice, the science, engineering, operations, and culture that have evolved over decades to make space exploration possible. It's a system-level answer, encompassing everything from fundamental physics to operational procedures, from launch to arrival, from planning to execution. And yet, for all the sophistication and complexity, the most fundamental reason remains simple. Space is mostly empty, and orbits are predictable. These two facts, more than any technology or procedure, explain why spacecraft can journey for decades without collision. Everything else, the tracking systems, the maneuver planning, the navigation instruments, the ground control networks, builds on this foundation, enhancing natural safety with human ingenuity. Rest well, knowing that above you, spacecraft trace invisible paths through the darkness, guided by laws of physics that have governed the cosmos since the beginning. They move with the precision of clockwork, through regions so empty that collision is almost unthinkable, toward destinations that await them across years and millions of miles. They are our emissaries to the solar system, traveling safely through the void because they understand the void's nature and navigate it with the care and precision it demands. Tomorrow, more spacecraft will launch, joining the fleet exploring our cosmic neighborhood. They'll follow carefully planned trajectories through the emptiness, avoiding the rare obstacles, arriving at distant worlds with precision measured in miles after journeys measured in millions. The cosmos will remain as it has always been: vast, empty, and governed by immutable laws. And spacecraft, built by human hands and guided by human minds, will continue their ancient dance through the void, threading the cosmic needle with an elegance that makes the impossible seem routine. Sweet dreams, fellow traveler. May your rest be undisturbed by collision, your path through the night as smooth as a spacecraft's trajectory through the void, your destination as certain as a probe's arrival at a distant world. The universe awaits our continued exploration, and the spacecraft we send are proving, mission by mission, year by year, that the cosmic ocean is navigable for those with knowledge, care, and the courage to venture into the beautiful emptiness beyond our world.